So we're going to be looking at the fourth and last exercise, remote sensing and raster GIS. And again, this is going to be due April 6th. So we'll change that right here. For those of you that are choosing to do it. And the purpose of the lab is to provide you with an indication or an introduction to basic remote sensing classification workflow and ways to assess what we call change detection in forested regions. So forest loss is really important today in that much of the natural forest and natural habitat is being lost to humans and human uses. In the example questions here, what you're interested in trying to find out is to classify from a remotely sensed image forest and non-forest classes. So to take a remotely sensed image that has multiple spectra, which is called a multispectral image, and use the information in the different bands of the multispectral image to use machine learning to classify or distinguish between forest and non-forest in images from two different time periods to determine how much forest has changed and where it has changed in more specifically. So it's approximately 15-year period we'll be interested in looking at here. So 2001 to 2016. And it's a small region in the southeast of Ottawa. And to do this, we'll be undertaking what's called post change detection classification. So that means we classify the two images, which are from two different sensors, and then we use the basic GIS functions to look at the forest class and see how the forest class has changed through time. So we have a 2001 image from the Landsat 7 ETM Plus sensor. ETM Plus meaning Enhanced Thematic Mapper. So that's the sensor that provides us with multispectral images at 30-meter resolution. So that means 30 times 30 equals 900 meters squared. So each cell is 900 meters square in size. And a second image from 2016 from RapidEye. And this has 5-meter multispectral resolution. So it has a higher resolution than the Landsat sensor. And we'll classify both of these using standard classification protocols in remote sensing. And that will provide us with a means to do a post-classification change detection, as I mentioned earlier. So we're going to skip down to the example questions now. The first example question, Q1, we did that in class. That's how to look at different band combinations of remotely sensed images. So we won't be doing that, or I won't be going over that in this particular lab exercise. Question 2 then is, how do we classify a remotely sensed image? And to classify remotely sensed images, we need training data. That's the first thing. Training data are examples of information classes found within the image. These are groups of pixels that correspond to a different information class. And we have two information classes that we're interested in. Forest is one information class, and non-forest is another information class. And so, looking at this example down here, in this figure 1, you can see that we have a green polygon, and the cells within that green polygon and their pixel values across all the different image bands correspond to an example of pixels that belong to the information class forest. And then we have a blue polygon down here in the bottom, and you can see that that's within a built-up area. And so all the pixel values across all the different bands in that polygon correspond to non-forest. And these graphs here just illustrate for each of those polygons the number of pixels found in each of the classes. So in this first one called B1 here, we can see that the forest pixels, there's a lot of them around values of there, which is I think around 60. I have to zoom in a bit more, like so. So around 50 to 60. And around 55, right in the middle there, you have a peak. So that 55 probably is an approximate average. So the average pixel values in band 1, the blue band of Landsat 7, is 55 for forest. In the same blue band, which is the first band, the pixel values for non-forest range from about 60 here to 60, 70, 80, 90. And it's a much more subdued peak, like you can see there. The average would be somewhere in the middle here, maybe approximately 75. And so the average pixel values for built-up regions, or generally this non-forest example, are around 75. And what's important for any given electromagnetic band, like the blue band here, the first one, is we're interested in seeing that there is separability. That means there is some gap, like you see right here, between our classes, our two classes of forest and non-forest. So there's no overlap between forest or non-forest, or if there is overlap, it's very small amounts of overlap in terms of the pixels. And this means we have good separation between forest and non-forest pixels within the blue band. Why is that important? Well, when we want to train a machine learning classifier to classify forest and non-forest, they'll learn best with examples of forest and non-forest that are pure. In other words, that are very different from each other within an electromagnetic band. If we look at the other four bands on this particular image, such as band 2, we also have good separability. So that's a good one. Band 1 is a good one. Band 3 has good separability. And you'll see that band 1, 2, and 3 are showing very similar types of examples with the same type of separations. But we get to band 4, and it's not so good. We have almost a complete overlap of non-forest with forest. And so this would be a band that would be not good for machine learning. Because it would cause to confuse it. Because in here, if you randomly choose a pixel that was within either of those two regions in this band, you wouldn't know or be able to tell whether it came from forest or non-forest simply by the information in a histogram form like this. You'd have to actually look at the map to find that out. So separability is very important when we're looking at classifying remotely sensed imagery. Now, once we have many examples of polygons that represent forest and non-forest, ArcGIS can create what's called a signature file, which summarizes the responses of pixels in the multispectral bands within what's called a signature file. So it looks at the separability, the commonalities between and within the bands, and puts them in a signature file, which is just a text file that looks like this. So it'll have the bands that are included, and then the names of the bands, being 1 to 6 in this example, and then how many cells there are being considered in total for each of the classes. So in this case, for the example above, there was 346 cells in the class 1, which was forest, and 149 cells in the non-forest. And then it gives the average between, or the average, or the means within each band for each class, as well as a covariance matrix down here, which is a way to assess the separability within the bands for the machine learning classifier. So once we have this training data, which are examples of each class called information classes that we want, and a signature file, we can then utilize a machine learning classifier to take each pixel within the image and classify it as forest or non-forest. So we go from our raw image here to assessing which bands are going to be useful in distinguishing between our information classes based on separability, to a signature file, and then using machine learning to a final thematic map containing forest and non-forest. And that's the process required for classification of a remotely sensed image that we're doing in this example question 1. So now we're going to be trying this on first the Landsat 7 image from 2001 August 25th, and it's called L7 2001 0825. I'll just be referring to it as L7. And it's in the Lecture 8 Remote Sensing Imagery Geodatabase. And you can add to ArcGIS Pro. So I'll go to my folders where I've already connected to my Lecture 8, go into the Remote Sensing folder, and then the Imagery Geodatabase, and here is L7 2001 0825. I'll just bring that in. And here we go. You can also expand, as I have done here, that particular image, and you will see that it is composed of a number of bands, 1, 2, 3, 4, 5, and 6. And so these are the bands, or the spectral bands, that make up the image. Now, before we can go any further, we have to make sure that we have Image Analyst and Spatial Analyst loaded, so you may have to go to Project tab and then Licensing, and you can scroll down to see if you have Image Analyst with a yes beside it and Spatial Analyst with a yes beside it. If not, you may have to click on Configure Your License Options and go in there, find those two in the list and change them to yes if they're not automatically saying yes right now. So right now mine are here. I have Image Analyst with a yes, So you may have to go here to enable them. So now we can continue on with what we're going to do here.